t-test in particular, there's a different test for different situations. So that's actually the hardest part about statistics, is choosing the correct test for your particular problem. And when you go to, like, say, machine learning or advanced statistics, it actually gets a lot harder. And sometimes you have to try multiple ways, but it's pretty straightforward. The t-test is used for a specific situation. So it is to compare means of two groups. So if you're calculating a mean of both groups, then obviously your data has to be continuous or numeric. So it has to be something that you can calculate a mean for. So you would only want to use this when you have two groups. You want to compare, see how they're different, or if one's greater than the other or one's less than the other, and compare those two samples with their means. So they have to be continuous or numeric. So a couple of possible research questions. I'm going to give an actual example in a little bit. So one question we might ask is the group one mean significantly different than the group 2 mean? This is probably, even if you're pretty sure that one's greater than the other, I would recommend in most cases looking at if they are different versus one greater than the other. So the p-value requirement for the difference is higher, so you'll be less likely to make an error. And I'm going to give a great example of one that you would totally expect to go the other direction, but we actually got the opposite result that might be intuitive to all of you. That's going to come in a little bit. So you never know. And one might be actually greater than the other group, but you would expect it the opposite direction. So I always recommend using this first option here. You're really sure that one group is going to have a higher mean than the other, then you can test if one group is significantly greater, or the mean is significantly greater than the other, and you can always also test if the mean of one group is significantly less. So, but the p-value cutoff is higher in those cases, and we as statisticians usually don't recommend doing that, because then your possibility for making an error goes up. So the most basic statistical tests, we don't always use them all that often because they have a lot of assumptions. So what an assumption is that if you cannot correctly apply a test results if you don't meet certain conditions. So, and sometimes those conditions are difficult to meet. So that's why we have a bunch of options, and that's also why it's difficult to choose a test. So one thing here is that when we're looking at a two-sample t-test, so we're looking at the difference in means, one group has to be independent of the other group. So basically, one group's values cannot depend on the other one, or they cannot be influenced by the other group. So that's something that you have to keep in mind when you're doing this. There are specific tests for when they are not independent. We're actually going to go over one of them. But this particular difference between two means t-test is one group has to be independent of the other. So we went a lot over the normal distribution in detail, but this is why we did it. In order to run a t-test, your data has to be normally distributed. There is a caveat to that. If you have over 30 observations in your sample size, the central limit theorem, which we went over, will apply, and you do not have to have normally distributed data. But if you have less than 30 observations in your data, it has to be normally distributed. T-test actually is a good test. It does a pretty good job of looking at statistical significance with small sample sizes. But if you have less than 30, it has to be normally distributed. So I added this picture right here. That is an example of 4 different normal distributions. They all have different standard errors and means, but they're all still normally distributed. So it's going to look like a bell curve. So that's why we went over the normal distribution, because you need it in order to decide what test you're going to run. So one way that you test for a normal distribution is actually my preferred way. It's called a QQ plot. So I will show what that looks like in a second. It will, if you have, when you plot it, it's, I'll show how to use it in R, it's in the R package, but it will plot your lines, your two values, and then it will look at if you see a straight line or something that doesn't have a specific pattern, if it's random, then it'll be normally distributed. If you're seeing a pattern like this or a pattern like this, it's not. So I'm going to come back to that slide in a second. So as you see here, this is what we've been seeing over and over and over again down here. So these would be our standard deviations. So 0 is going to be our mean. So this would be a z-score in particular. So our normal, it'd be our normal distribution. And then we have over here, if you can see, the actual values in our data. So what's showing here, I'm going to give an example. We're going to compare counties that did expand Medicaid and counties that did not expand Medicaid, and see how much their enrollment differs between states. So if you saw something like this, these are the normality bounds. You see this dotted line here. You can see that some values lie outside of those bounds, and it would probably be good practice, unless you have a good reason not to. If it's anywhere outside of that -3, you should probably remove them as outliers. I'm not going to do that today, but it's good practice. A lot of times, and if you have less tolerance for error, you might even want to go and do anywhere between 2.5 standard deviations out. But you're going to see here that some values lie out of that like threshold, but it's, for the most part, we're not seeing a pattern here. That we're just seeing a straight line. And I'm going to give an example of one that it would not be normally distributed in just a second. So actually gonna skip ahead to that just so you can see the difference. I should have put that slide.
Ask a question.
Yes.
Considered a point for a norm quantity. Like how do you what makes the X point?
That's a z-score. So that's what we went over, yeah. So, or there's a t distribution, and in some cases it's used with that as well, but it's very similar to a z-score. It's standardizing your values. So the z-score is going to be on the bottom, and the actual points are going to be on the top. So this on the right, we would definitely want to proceed with caution. In this case, we have more than 30 observations, so it's not going to matter in practice. But if you had less than 30 observations and you saw something that looked like the graph on the right, you would probably not want to run a t-test, because you're seeing it's clearly a curve and not a straight line. So there's a little bit of wiggle room here, but if you see a pattern, it's not normally distributed. So I'm going to go over, there's another way to test for a normal distribution that's a little less, okay, so if you have a small set of data, so I'd say within 50 observations, maybe even 100, you can run a Shapiro-Wilk test. So a Shapiro-Wilk test basically tests for normality, but basically when it's looking at your data, it adds something on every time something's not normally distributed. So if you think about that, if you have thousands of observations, even if your data is normally distributed, there's probably going to be several outliers, and each of those outliers is going to add on to the value that is used to test that normal distribution. So I found that if you don't have a small sample size, this doesn't work. So I would not use that unless you have a small sample size. I'm going to show you what it looks like in a second. But that's how you would test normality. Okay, so I'm going to go in. The code is on the shared drive as usual. So if you'd like to follow along with the code, you're welcome to bring it up. So over here. Mm-hmm.
The sample size is lower and the big standard practice.
Yeah, you don't have to, but I generally do just to know my data and know what I'm working with. I and most statisticians would agree with this. It's good to run extra just because if something comes up later and you need to know, it's good to know what it looks like. So that's what every piece of advice that any statistician will give you is graph it first. Look at it, dig in, and make box plots. You can do histograms. You can actually look at bar graphs. You want to have a really good idea of what your data looks like before you run anything. So that's a great piece of advice. Thank you for bringing it up. So before you run anything that we're going over, you would want to graph this, look for outliers, look to see what type of distribution you have. Is it skewed in one direction versus the other? Because all these pieces of information might actually affect what test you use. And it's not just a normal distribution that has that affects what test we use. And we'll go over more about that. But I recommend just erring on the side of knowing everything about your data. But it's not gonna, in this particular case, matter whether we use a t-test for our test or not if we have over 30 values. So, but I do recommend running it anyway. So if you do not have CAR installed, I have it commented out here. I'll make sure you run that. If you do not have it installed already, just take out that this and run that. I can't run it because it's gonna error out on me. So I'm going to load this library. All this is getting rid of scientific notation because a lot of people in this room might not know scientific notation. I always turn it off because it's very difficult to read. So we have 3 data sets that we're using. All of these should be in the shared drive. They're already cleaned. Like I said, in general, I'm going to clean the data before I give it to you because this is not a programming class. That you're welcome to go and take online. So this is going to be based on statistics, and you're not going to really have to know how to do much programming for this class. I do most of the hard stuff for you. So, if you've ever taken a programming class, this is an example of when you use a factor variable. I am going to explain what that is. So before I run that, if we're going to pull this up, so Medicaid expansion data frame. I actually should get rid of this just so you can see what it should look like. Just because my data, I don't want to look different. So if you run the first couple of lines, you're going to see something that looks like this. So when I open this up, I am going to look at whether a county has Medicaid expansion or does not have Medicaid expansion in the Affordable Care Act that was passed several years ago. So this is what the variable we're going to use for a t-test. And you'll see that some expanded and some didn't expand. I'm just sorting there. So this is a data frame also. So you'll see that it looks very similar to what you would see in Excel. So that's, if I ever refer to a data frame, it's just data in a tabular format or something that you would see in Excel. So if we're looking at our Medicaid expansion data frame, which is what we're using for our analysis, you scroll down, you'll see that there is a factor with 2 levels. So I'm going to actually expand this. So this will make more sense when we're looking. So you're seeing this is a label. It is not the actual value. On the back end, it's labeled as a 1. And what's in the quotes is a label on your data. So a factor is basically, you have a string value, but it's on the back end, it's coded as a number. So you'll see that expanded Medicaid will be 8 in this particular case, if you looked at it. But you'll see here, it looks like, you can just see the labels. And if you have that, you'll see a factor for 2 levels. So going back here, I'm going to reload this data just because I put strings as factors equals false here. So that means it's not going to be a factor. The way this is how you know if it's a factor or not. So it'll have character here versus factor. And you know that written here is actually coded as did not expand Medicaid in that case. So this would be a use case where you would want to use a factor variable. Because it will have to coerce your data or force it to be a factor anyway. So it's best to do it that way. And if you want to learn more about that, take my programming class, or there's a self-guided tutorial online already about that. All right, so we are going to use that. I'm going to have you try an example. It'll be in the water quality and Barton Creek versus Lady Bird Lake. It dissolved oxygen is what we'll be looking at. And this is a fake data set I just got online, so we could do a specific test with it. That's the example of a reaction time before 2 beers and reaction time after 2 beers that I gave earlier. So we have this, we have our factor variable now. So for those of you who've never been here, I always write in the comments what I'm doing. I would not focus on understanding the code unless you take the programming class. If you look, I will always explain exactly what the piece of code is in this comment above. So this particular case, we want to make a QQ plot like I talked about before. We're going to first look at, you'll see here, percent on public insurance less than 19. So that means, and I try to use a descriptive name, which you always should, that's the percent on Medicaid or Medicare insurance that are less than 19 years of age. The reason someone below 19 would be on Medicare is if they have a disability. So that is included in this. So basically government provided insurance. So I pulled that data for us. Now I'm going to run that QQ plot. And then it has to adjust. So when you open it, it's going to look something like this. We're seeing this here. This is definitely normally distributed. We're not seeing much outside of this threshold. We're not seeing any type of pattern. This is definitely, we will look at this and say, okay. And again, it doesn't in practicality matter because we have a lot of observations, but I want to explain and show how to do it anyway. So the next one we're going to look at is the percent on public insurance from age 19 to 64. So customarily, those individuals would be on Medicaid. So we're going to run that QQ plot here. So now our graphics have adjusted. Say I did not, I had a smaller sample size than 30, I would probably not, I would want to run a t-test in that. This is, I would not call normally distributed in this case, because we're seeing a clear pattern there. So that's how you read a QQ plot. So I'm going to have you just take a look at this. When you are supposed to run this, I'm going to go over several examples. This will be the data frame that you're working with. This will be the variable you want to test, and there's also a lot of information slides if you need help. And then you just write the group that you want to test. So within this data frame, you would test Medicaid expand. So the way I'm trying to do this is you don't necessarily have to understand the code, but you'll be able to follow the pattern from the earlier when you try it yourself. But there's going to be a lot more things. Question. Go ahead.
On for line 21, when you read it, you said that was not correct. Second one was 16 or 19.
The one that's up now is not. So it would be the right that is not normal. The left is. I would call that yes, but over here, not. So that's the counties that have expanded Medicaid in that case. So if you had less than 30 values, I probably wouldn't run a t-test in that case. But just so you know what it looks like. So now I'll go back into the PowerPoint, and hopefully I will, just because I'm going to go back and forth with the code, this is the best way. I have to kind of stay out of the PowerPoint for a little bit, just so I don't have to spend the time going in and out of it. So that is the normality assumption. So we have to either have over 30 or we have to have normal data. That's the first assumption for a t-test. The next one is homogeneity of variances. So we went over the standard deviation a couple of weeks ago. So the standard deviation is looking at the spread of your data. The difference between the standard deviation and the variance is if we calculate the standard deviation, if we squared that, that would equal the variance. So, or if we took a square root of the variance, we would get the standard deviation. So that's how and why another reason why I gave you that. So this actually shows you how the variance is calculated. So we have our value 1, we would find the mean of everything first. And then we would take value 1 minus the mean and square that value. Value 2 minus the mean, square that value. Value 3 minus the mean, square that value. Go all the way through all of your values, and then you would add them up, and then that would be your numerator. The number of observations is in the denominator. So we can think of this as the mean variance. In this particular case, it's kind of like that. But that's what we would call variance, and that's how we would calculate it. I'm not going to make you do that by hand. I just want you to know, and you can go back and look at this, and if you don't understand. But the second assumption is your groups have to have equal variance, or within a certain threshold, they have to be equal. So in order to test that, we would want to use a Levene's test. This one tends to work whether your data is big or small, it doesn't matter. So that is what a Levene's test is. So what if your variances are not equal? There is a certain value inside the t-test function that we'll have to use a little bit differently, and I'll show that in a little. But it's basically, this is an example of knowing your data so you can determine which test is best. And I'll explain more about that in a little bit. So before we move on to how to test the different variances, are there any questions so far? Go ahead.
The variances must be roughly equal, so what?
Yeah, we're about to get to that. You would test with the Levene's test. So except for how to test it, are there any questions of what I've already gone over? Okay. So this is how you would test or use the Levene's test. This is also in the car package, I believe. So you have to have that loaded. So the Levene's test, this is the particular function we would want to use. Remember, R is case sensitive. So if you use Levene test all lowercase, you will be, I think there is a function that does that, but it will probably error out because it probably won't be in the correct package. So you have to keep in mind if it's capital or lowercase. So that's something you just have to watch. And if you didn't know what to run, you would Google this and then maybe look at the help file. So we're seeing here, we have our dependent variable. So that's basically what we are going to look at. In this case, it would be the numbers of the percent on public insurance that are less than 19 years of age. So that's those are the values we are actually testing. Then we'll put a tilde, and then the next one will be the grouping variable, or the groups that we want to differentiate between. So we're doing expanded Medicaid and did not expand Medicaid, and it's counting. Is at a county level, this data. And then you'll put data equals and the name of your data frame. In this case, it's this. So this is what is going to come out. So once you put all that in, it's going to come out. So another reason to learn p-values. So with UC, I would, in this case, this is a great example of when you would not want to, in my opinion, it's all going to be, a different statistician will tell you something different, possibly. I would use 0.10 as a cutoff for the p-value here. So if it's below 0.10, I would use that as my cutoff to do a modified test, which I'll show you how to do in a little bit. This case, it's nowhere near 0.10, it's above that, so we know that our variances are roughly equal. So we look at that p-value from the Levene's test in order to test for equal variances. So that's what we would do here. So does that make sense? All right, so I'm going to go real quickly in here and show you what this looks like. So I'm going to give 2 examples here, and I will scroll up here.
I have a question.
Mm-hmm.
Each time you have 2 plots side by side, what's on the left and what's on the right?
The labels are up at the top. So the Levene's test, I just showed how this was written out. Just to recap, this is the variables, the variable that you're testing, the actual values inside your groups. This is our group, and that is our data. So we're gonna run this. This is for. So the next one we're gonna run is Levine's test for percent public insurance, ages 19 to 64. You're seeing down here, this is way below 0.10. So the variances are not equal here. So we would have to modify our test, show you how to do that.
I just want to point out that your comment says that it is greater than 0.05.
If it's greater than 0.10, you're good to go.
No, but in that comment on line 28, it says there's not equal variances because the p-value is greater.
It's because it's less than. This is the less than sign. Yeah.
That's put on the comment on line 28.
So this is what it's referring to. They're not equal. So after you run that, you'll see
It's not equal because in that comment it says because the p-value is greater. Or it should
Oh,
be
yeah. Thank you. All right. So yeah, I'm all right. That was a typo. Thank you. Appreciate it. So we have that point if it's below that 0.10, and it won't even have these significant codes. So if you look up here, when we were nowhere close to any of the 0.10, it didn't even like print those significance codes because they're not going to be applicable. That's another thing that you'll see a difference when you run it. So down here, we're seeing that yes, our variances are definitely not equal in that second case. So I'm going to run a t-test, but I'm going to have to run it differently. So first, I'm going to go over the entire process of running a t-test for things that do have equal variances. The next example will show you how to do it when they do not. So to hold those questions about non-equal variances until we're done going through the normal or the standard t-test. So in this particular case, as we saw, that the percent public insurance less than 19, those do have equal variances. So we should be good to go in that case. So we're going to run just a normal t-test, the standard. It's called a student's t-test in this case. So we would want to use that t-test function. It's not in a package. It's already loaded into R automatically. So this is one you're not going to have to worry about that. So you'll see here, this grid looks very similar to the Levine's test. So we have what we want to test, the values or a dependent variable, the values in our groups that we want to look at. We have our grouping variable, data equals Medicaid expansion.df, and we put var dot equals true. So that is how we modify it to say that our variances are equal. The default is false. The reason for that is if you have false written, it's going to run something that is more conservative. So they want to default it to the test that'll have less error. It'll be harder to get statistical significance, but it's going to give you less errors. So your variance equals, you have to write that out in because it's not the default. So that's how you would write it in here. And when you're going through your exercise, you can come back to this and it'll tell you what to do. I am going to show, I've showed this before, but I just want to reiterate. This is how you get a test help file up. So say you wanted to run a t-test, you knew it's the t.test function, but I have no idea how to structure it. You press enter, go over here. This is our help file. So we'll see here the t.test function, and then we have our x variable, our y variable. You'll see why you might want to use y in a little bit. In this case, the default is null, or it doesn't have anything in the y value. So the alternative, two-sided, less, greater, two-sided is the default. They usually write the default there. You would have to scroll down to see that. So you'll see the default is two-sided. So if you didn't know what the default, it would say either here or up here. You'll see variance equals and it has false. That means the default is false. So, and it will give you, there's a lot of things we're not using in here. So if there is no default written, then you have to put the value in or it will throw an error. So you only have to put in the x values. So that value you're testing tilde grouping variable. Because there is no default in this particular example. All right. So we have now exactly what I showed you. This is the code that we looked at. So in this case, I'm going to run the t-test. It will set it equal to this variable. You can also not include that and it will just print the results, but I would save them. So this, putting it equal to this value, saves your results. So we're going to run that t-test. And then if we run the next line, it's going to print it. So these are our results. So if you have equal variances, it'll say 2 sample t-tests at the top. I'll show you what it'll say if you do not in a little bit. So we have our p-value here. So it's less than, if we consider 0.01 to be highly significant. So anything below that, so this is very significant. And this will be in the opposite direction that you would expect. So I'm going to go back. So this is a great example of why you should run a difference test versus a greater than or equal to. So, and I was actually even surprised by this, and I worked in healthcare. So, but when I looked into it more, it made sense. I'm going to go in here. So zoom in there. So why we're seeing the mean in group expanded Medicaid, so the percentage on Medicaid is lower in the expanded group versus the non-expanded group. Why could that be? That doesn't intuitively make sense. First off, before Medicaid expansion was passed, all states pretty much had high thresholds for kids. It was, the CHIP was passed, Medicaid was passed, even in a very conservative state like Missouri, it was 300% of poverty. So whereas parents were 12% of poverty. So before anything was passed, they were all already high. So in every state, not necessarily in like liberal versus conservative, they were all that way. So there's another reason. So there are actually the majority of states have expanded Medicaid at this point. So, but some have not, as you know. So I had another theory. So we have whatever number is left over that has not expanded Medicaid. I forgot you'll have to put this up here and install that package too. I apologize. I always have it installed, so I use dplyr for everything. So if we're gonna look down here, t-test for adults. So it's gonna print, all this is a summary table. So I looked at the mean below the poverty line in states that did not expand Medicaid, and the mean poverty line below the poverty line in those that did. You're seeing that poverty is higher in those that did not expand Medicaid. So by default, if you're not controlling for poverty, we're going to go over how you would do that with another statistical test later on, once we've gotten the hang of this. So what we're just looking is the mean greater or less than. In this case, because the poverty level is higher, that is why our Medicaid enrollment is higher in states that did not expand Medicaid, because they were already high for everybody. So that should explain to you. And this is an example you would always want to run difference versus greater than or less than. You wouldn't, unless you had a lot of knowledge, you would not think that this is how it would look. So because I ran a difference, then it was easier to show that this was our final conclusion versus something else. So that gives a great example of being careful. So I will go back in, and hopefully that makes sense to us now and that's the only reason I know all that is I used to work in health policy. So that would be why I would know. Okay, we've already seen this. I gave this example. So this is adults, so 19 to 64. It's the amount on Medicaid as well. So you'll see here, the labels are at the top, did not expand Medicaid, expanded Medicaid. And you'll see the same exact structure below. Okay, we already looked at this. We tested for equal variances. In this case, this is the one that we saw that did not have equal variances. So this one should look exactly like I just showed in the code. And now we'll run our t-test. So if you do not have equal variances, it's really easy to make it, it'll adjust it. If you just put in var.equal equals false. So it's then going to assume that you do not have equal variances. So I'll go in here. And so we know that from our Levine's test, so then we change our t-test. So one other thing I want to show, so we had that t-test that we ran. We went over confidence intervals last week. So I'm going to show what that confidence interval would look like. So this is, we are looking at that mean value, and you would find that our critical value or the actual mean will lie between these two numbers most of the time. So that is going to come out of here. So that it's between those two percentages. So this would be looking at the difference, by the way. So the actual percentage, and I can open this real quick just so you can see and also get a better look at the data. So you'll see that these numbers are a lot bigger than what we're seeing in that t-test. So it's actually looking, because we're looking at a difference, it's saying that there is between a 2.7% difference between the two groups and about 0.6. So our mean difference lies between those two values 95% of the time. And when we use a alpha value of 5. And in this case, I actually wanted to show you as well what a 90% confidence interval would look like. So if you want to change the confidence level or the requirement, you would put conf.level equals 0.9 in this case. So I wanted to show you the difference so I can reiterate what a confidence interval is. So in this case, we're seeing up here, our confidence intervals go from 2.7 to 4.6. If you look down here, it's narrower. Why would that be? Because there we are giving less room for error for the 95% confidence interval, so it's always going to be wider than the 90% confidence interval because we're giving more room for error with the 90%. So that is the difference between those two. I'm going to go over this output and then I'm going to give a 5-minute break. So in this case, we put variances equals false in this case. A variance var dot equals false. When you do that, it's going to put a Welch's two-sample t-test at the top. That's just the name of the test with non-equal variances. So we'll see that this p-value is still very significant in this case. What it's going to do is it's going to adjust our standard errors and our degrees of freedom, which is our sample size -1. It's going to make them, adjust them, so it'll give you a more conservative result. So it'll be harder to get statistical significance. So it's going to adjust those. It's out of the scope to show you exactly how they do that. But what you need to know is that it's going to make it harder to achieve significance. And you're going to see your confidence interval here as well. So you're going to see the mean in the group that expanded Medicaid for this still in children. Yeah. Oh, I did not run the t-test yet. That's why it's still in children. So that would be child 95. I wanted to show what it would look like if we. So this is what I wanted to run. So this is adults. So this is the Welch's two-sample t-test. I think I made a typo at the top. I'll fix it in the break. But so you're seeing that the mean in that expanded Medicaid, the mean of the adults on Medicaid is almost 20% in states that expanded Medicaid. It's about 16% in the states that did not. That's because their thresholds for your income are lower. And I believe it's still only 12% in Missouri, which is where I just came from. So you have to basically have no assets at all in order to qualify. So another thing about confidence intervals, in this case, we're showing that the mean in expanded Medicaid is significantly greater than when it did not expand Medicaid. So it's going to subtract this from this. So that's why we're seeing negative values. This is looking at the difference, as we remember. If your value is, we're looking at that difference. If the 0 lies inside your confidence interval, it will not be statistically significant. You see 0 in your confidence interval, you know it's not statistically significant. So that's saying it could be 0 difference between the two. If 0 is outside of it, it's significant. So that's what you can look at here. So this is our Welch's 2 sample, and that's when variances are not